Good afternoon, everyone, and welcome to Algorithms and Data Structures. Today, I saw quite some students in the lab in the morning, and there were some online discussing the coursework. And last week, we did sorting. So this is the coursework you can do by now. And today, we're looking at another fundamental data structure, which is trees. After trees, we still have maps and hash tables left, and then we have done all those essential data structures in this course. And trees are also a kind of graph, but with certain constraints. And we'll be looking, first of all, in the simplest kinds of trees possible, so-called binary trees. And we'll see how we can work with binary trees and how we can traverse them. And then we'll see some more advanced types of trees that are sorted. And then we will look into decision trees. The first three bullets are something we're doing today. And in the next lecture, we'll be doing decision trees and how to learn them. So we'll be seeing some machine learning, but I'll say more about this in the next lecture. We're starting now with what trees actually are. And trees are a recursive data structure that store their elements in a hierarchy. And there are a couple of properties, and we'll introduce these terms now. So we say we have a top node in the tree, and this is called the root of the tree. And such a root can be the parent node of more nodes, which would be then the children of the root. And a node that is a parent would have then 0 or more children. If it has no children, is not really a parent node anymore. Nodes that don't have any children are called leaves. They're at the end of the tree. And every node has exactly one parent node. That's a constraint. And that's where these kind of graphs have their main distinction from, say, generic graphs, that every node has exactly one parent, not multiple parents, except the root. The root doesn't have any parent nodes. And a node will also contain data. And this is a recursive data structure because we can apply this concept over and over again, that the root has children and those children have children and so forth. So it's a recursive data structure. And for us, in order to be able to work with it, it's very helpful if we know about recursion already. And recursion is something we did in the previous weeks. Then we applied it to sorting. And today we're applying recursion to trees. And this could be a sample tree. So this is about some electronic or a company about electronics, and the company has an R&D section. So we have the node, and the node would have, or the root would have multiple children, which are the departments within the company: R&D, sales, purchasing, manufacturing. And for manufacturing, we would have multiple sub-departments, like we manufacture TVs, CDs, tuners, and sales has 2 children, domestic and international. Domestic and R&D, for example, are leaves because they don't have any further children. And then international has more children and so forth. So we see this is a recursive data structure. And whatever node we look at, for example, Asia or CD or purchasing, they all have exactly one parent. And this is one of the key properties of a tree that makes it more specialized than a generic graph. The root doesn't have any parents. Now, what are trees useful for? For you as an end user, if you use a computer and you have file directories, eventually your file system is a tree because you have directories and they have subdirectories and so forth, and you store files in your directory, and a file is a leaf then because it doesn't have any subfiles, but for that you would pick another directory. if you do object orientation, you may have inheritance hierarchies. So you have classes inheriting from others, and those that inherit are the children of the superclass. We've seen exceptions in this course, and we saw that we can also do inheritance in an exception hierarchy. So an exception hierarchy can also be represented as a tree. Then there are search trees. This is something we'll be looking at today. Search trees, they store data in a sorted way, so we can search the data very efficiently. So we'll contrast this a bit to sorting from the last week. Then when you have databases or database management systems, they are used to store and retrieve and manipulate large amounts of data. So you need to represent your data efficiently in a database. Trees are typically used for this. We'll see later more about those kind of trees. And when you take a course on databases, which is, I think, next semester in your schedule, then you'll see trees again. There are also decision trees, so a tree that we can follow in order to make decisions based on our input. And this is something we'll be focusing on in the second part of this chapter, because we will look at decision trees and we will see how we can actually learn them from data. So we'll be discussing a machine learning algorithm, which is relevant to all of you, not just the AI students, also the cybersecurity students, because knowing about machine learning is now probably a very good thing if you're looking for a high-paid job. And there are plenty of machine learning applications also towards cybersecurity. And trees are also often a foundation for more complex data structures, but that's something we'll also be seeing. Now, when we look at trees, it's helpful that we first of all look at the abstract data type. We've seen quite a few abstract data types throughout this course, and now we'll be seeing one for a tree. So in a tree abstract data type, we're using the concept of a position, which is an abstraction for a node of the tree. And an element or a value is stored at each position, and the position satisfies this parent-children relationship that we have just seen. And if we have a position P, we can get its element value. So dot element is a method, and we can get the element or the value that is stored at position P. Now, when we have a tree that we denote by a capital T, we need to look at its methods for accessing the tree. And typically the way we store a tree is we have a position, where before we saw a node, and we have a root, and this is the one we're keeping the reference to. And for our tree, we can get its root element. So dot root returns the position of the root of our tree, or none if the tree is simply empty. And we can also check if a certain position is a root in our tree, which returns true or false. And for our tree, we can pass P to the parent method, and this returns the position of the parent of a position P, or none if P is the root, because the root doesn't have any parent. These are the essential ones, and then there are obviously more methods that our abstract data type may have. Like we could return the number of children of a position in our tree. We could get a reference to the children of a position, which can be multiple. And later we will see that for this, we need a concept of an iterator, which is something you may have come across in Python already. And you were asked to do some readings about this when the term started. And today we will emphasize this. We can also check if a position is a leaf of our tree. The length of the tree is the number of positions and therefore the elements that are contained in the tree. We can check if the tree is empty. That means we have nothing in the tree actually. We can also generate an iterator over all the positions in the tree. And we can also have a generator where we can generate an iteration of all the elements of the tree. We'll later see this distinction, and the concept of an iterator is something you have used actually all the time in Python, and today we will also emphasize this a bit in Python. Now, as you know, I really like the Goodrich book. The Goodrich book, even though it's now more than 10 years old, it's a really good book, provides, I think, a very good introduction to algorithms and data structures and lots of code. And I use quite some of the code samples from the Goodrich book. However, there is one chapter where I don't refer a lot to the Goodrich book, and this is in fact the trees chapter. If you look into the Goodrich book, you will obviously find code samples for trees. But I feel the Goodrich book provides very generic implementations of our abstract data type tree. Those are extremely generic implementations with a huge inheritance hierarchy. But the only problem is, if you check the book, that's a lot of code eventually. And I like very short code examples that show us the essence. And that's why when I prepared this course 4 or 5 years ago, I felt if I use the Goodrich book here, this actually leads to lots of unnecessary code that is maybe highly generic, but it doesn't really help us to understand the concepts we aim to discuss in this course. And that's why the Goodrich book can be very helpful for further reading if you want to learn more about trees. But here in this chapter, I'm not using it actually a lot, but I'm using sort of my own implementations that are extremely short and still show us the key essence without getting lost in an inheritance hierarchy. Now we will look at the concept of a binary tree. And a binary tree is quite simple. And a binary tree has the following properties, and we say a node has at most 2 children. So a node can have no children, then it's a leaf. It can have a left child or a right child or both. And we will also assume there is a certain order in it. So we have a certain value in our node, for example, value 10. Then the value in the left child, if we have one, needs to be less than 10. And for the right child, that value needs to be greater than 10. We're now doing this for integers, but we could also pick totally different values that we can somehow bring into order. It can be characters, it can be objects, but for objects, we would need to define how we actually order them. But we're starting today with integers because those are most easy to actually sort. But we can also have simply no children, or only a left child or a right child, or both, whatever. But we always then assume that if we have our left child, the value in there must be less than the value in the node, and the value in the right child needs to be greater than the value in the node. And these children, they may also have children, and there we apply the same property. And that's why a binary tree is sorted, because we have some value in the root. Everything that is to the left of the root is less than the value in the root, and everything that is to the right of the root is actually greater than the root. And these binary trees, they're the most frequently used type of trees, I feel. We can now implement them. And once we implement binary trees, so we will see how we can sort data in there. It's a sorted data structure, how we can check for a value in the data structure. And then we see some things that maybe go easy and some things that maybe don't go that easy. And we'll see how we can then improve by using more advanced sorted trees. And this is sometimes then called a search tree, because it's a sorted tree and we can search in it very efficiently. Another example of a binary tree could be something like this. If you have a mathematical expression of a binary tree, you could also express this as a tree. So for example, we have a minus and we calculate some term, and that term minus another term is our result. And we could say, well, the left side is actually a division, and the division is composed of a multiplication and an addition. And this multiplication is actually an addition multiplied by 3. So the 3 is a leaf. And this addition is 3 plus 1. So this is 4 times 3. So 4 times 3 is 12. We divide 12 by something. And this something is, we say, well, it's 9 minus 5, which is 4. 4 plus 2 is 6. So 12 divided by 6, this is a 2. And you could do the same for the right. And this is a representation of a mathematical term. And this kind of representation you would, for example, come across if you build a compiler, for example, because when you build a compiler, you want to, first of all, go through your source code, and you want to do a first step, which is called delexing, where you have the individual pieces in your code, and you just want to separate them. So for example, one would be a string, then you would have an integer, maybe some keywords. And then in the actual parsing, you want to bring some meaning to this, and you actually build such a so-called parse tree. And when you have the tree, you're checking syntax, and then once you have built a tree, you can also evaluate the tree. And like this, you would then get, for such a parse tree, you would then get the result once you evaluate it. Now, building a compiler is obviously something quite tough, at least if you do this for some coding language like Python, C, or some subset of these languages. But if you build, I don't know, a piece of code to evaluate terms like these here, you would need some of these properties of a compiler at least to evaluate them. But this is just an example, or just an illustration of the binary tree. And the left child means we have something in the left, and then we apply this operation to the left and right. So this one minus this one here. So we have an order in here, because the order matters, because it matters if we take the left and subtract the right, or vice versa, we will probably get a different result. So order is important. And I'll show you now how we can implement a tree, and how we can actually implement not just a tree, but a binary tree, and how we can bring some order into all of this. So we need a class node, and for our node, we need an initializer, and we pass some data that we want to store in that node. Could be some value, could be an integer, could be a string, whatever. So I want to store this in my node, but on top of this, my node will also have a left and right child, and initially they are none. So it's like a null pointer or none reference. And when we initialize our first node, that would be then, or our first node object, that would be the root. And we will later work on an example and see what this looks like. And now, once we have created our first object of node, our root, we want to insert something, because the root stores now some value, for example, 10. And it's a binary tree, so I have a left and right child, or just one of them, or both, or none. But this is the order: first left and then right. And now I want to insert something. And so I always keep the reference to the root object, which is an object of class none, and then I would call insert. And now, this is obviously a very simple implementation of a binary tree, and there's lots of things that may reduce efficiency, but we're starting with the most simple implementation possible. And we are first of all wondering, is something stored in data or not? That is either the case or not. And say if we have nothing stored in our data, so if we had just passed a none value or something like this, then we actually put that value into, so when we insert a value and our data that we had initialized here is actually none, then we're just putting, by convenience, the data in there. But when we initialize our node objects, it would be typically more common we pass a concrete value for data. So this else here is probably not that common. And now I said we need to put the data into the left or the right child, depending on if that value we are putting in is less than or greater than the value we have in our node, because this is the value we have in our node object. So we could check the new data I want to enter or insert if this is less than what I'm storing in my node. And I could say, well, then I'm initializing my left with a new node where I'm storing the data, because now I'm building this recursive data structure. So I say, well, my left child will now contain the reference to a new node object where I'm putting in the data I'm trying to insert. But it isn't that easy, in fact, because maybe we have already before inserted something in there and we have already started building the tree slowly. So I cannot just create a new node object and put it into left, because maybe there is something already in left. Like, for example, I have a value 10 in my root. Then the left child has the value 5. And now I want to insert, say, a 3, for example. So I cannot just put that 3 as the left child of the root, because the left child of the root is already a 5. So I need to go to the left child and then try to insert it there in the right order. So I need to make this a little bit more sophisticated. So I need to check if the left is actually none. And if the left is none, there is nothing in the left. So I can simply do what I was planning to do here. But if there is a left child already, then I need recursion, because then I'm saying I'm looking at the left child and there I'm trying to insert a value. And then this is a recursive call. And then if the left child has no left child, then I'll try to insert it there. Otherwise, maybe if there's already a child, I need to go somewhere else and further down. So that's why we implement this quite conveniently using recursion. And here you see we were only able to discuss trees reasonably once we had actually discussed recursion in this course, because without recursion, it would be still possible to write these algorithms for trees, but it's certainly far less convenient and definitely more difficult to understand. So we have now this case here, or we've always had the case where the data that we try to insert is less than what we have in our node. Now we can look at the other case where the data we're trying to insert is actually greater than the value we have in our node. So I just need to do the same as before, but I need to do this with the right child, because if I'm putting now, say, I have my root with value 10 and I'm trying to insert value 20, for example, I need to do this in the right. And again, I'm checking if the right is none, and so there's no child in the right, and then I'm perfectly fine, because then I can create just a new object of class node and put it in the right. However, if there's already a right child, I again need to look at the right child and say, well, I'm trying to insert it there, and I have a recursive call, and then it tries to find the right spot. And then say if I have value 15 already in the right, and I'm trying to insert value 20, then I have the recursive call on the right child, and there we will now try to create a new child in order to store this. Are you okay with recursion here and with understanding what we're trying to do? We're just trying to build maybe some reaction here with a chat, thumbs up, thumbs down, whatever. If you got that idea that I'm trying to put the value in the right spot in this tree. This is not maybe something that will lead to the smallest tree possible. With this kind of approach, it could actually lead to quite an inefficient tree, but this is something we'll be investigating later. And we can do a few more things, taking advantage of this structure. We can now try to find a value, and we can check if a value actually exists in our tree, and we could check. And there's a good question here that we got in the chat. I thought about it, but then I forgot to mention it. We have an if and an else if. What happens if data has the same value as the node? Right here, I wouldn't be doing anything because it's already added to the tree. And with my tree, I would assume that each value could only exist once, not twice. But probably it would be smarter to handle this in some kind of different way. But imagine this tree here being some kind of set where I can, or like an ordered set, or an ordered tree, but a value can only, or the same value can only be once in that tree. It's a simplified tree. Later we'll look at more complex ones that can handle this. But just with this initial implementation, we try to keep it as simple as possible. And also when we are now trying to find the value, we are keeping this a little bit simple, but it's just our initial implementation. So we are trying to find our value, and we check if our value is less than the data or the value we have stored in our node. And this is the first one. Then we have another one where we are checking if the value is, or the alternative where we're checking if the value is greater than what I'm storing in here in the node. Otherwise, so there are three options. The value is less than what we store in our node, greater than, or the third option is, well, it's actually the value we have in our node. Obviously, you could write this condition in a slightly different way to reproduce the same behavior. But here we'll say if the value is less than what we store in our node, greater than, and if none of these conditions is true, then, well, the value we're looking for is actually the value we're storing in our node. Now, this find value also works in a recursive way, and we will try this now. We will check if our left is none. So if the value is less than our value in the node, and there is nothing in the left, then this value cannot exist in my tree, because if it existed, it would be in the left, but there's nothing in the left. So I'm returning false. However, if there is something in the left, that means we have another node in the left. So we need to take advantage of recursion. And we say, well, I'm looking into the left, doing a recursive call, or I'm looking into the left, and there I'm calling find value, and or on that element, for the value I'm looking for. This will return either true or false, and whatever this call here is returning, I'm returning that. Now we've done this for the left. We also need to do exactly the same for the right. So we are checking if the right is none. And if that's the case here, I'm also returning false because I'm looking for a value that is greater than what I have in my node. If there's nothing in the right, it cannot exist. Otherwise, again, I'm taking advantage of this recursive structure and I'm saying self.write find value, and I'm looking for that value. So this is at least a very simple implementation, and we can try this out now, and I can say, well, I'm creating a root where I have a node. The node is the root, and I'm now not using integers, I'm using characters, but characters, I can also easily sort them, and I can say an f has a certain integer value as a correspondence, and the b is less than an f, while an h is greater than an f. And I can now, for example, try this out and say I'm inserting an a, I'm inserting, say, a b, and I'm inserting a g. And now we can look at this root. So the root is just a reference, but before we said this is called data. So an f is stored in the root. In the left of the root, you can probably guess where it was sorted in. So because we started with an f and then we're inserting an a. So if we look into the left and that value, so the reference was called data, then the a is stored in the left child of the root. And then we also sorted a b in. That means if we look at the left, it has a right child, and that data is the b, because the b is greater than a, so it must be in the right child. And if we look at our original root, we sorted in also g, so the right neighbor of the root, because the root has value f, and then we sorted in a g, so that must be the right child of the root. And that right child has no left and no right child, otherwise we would see a reference here. This is a very simple demo of what we have done before. And we can also obviously use the find value. We can say root.find value, and we want to find if there's an a, yes, there is a b in it. Is there a c in it? No, we didn't sort this in. So this seems to work so far. And there is a question here about our else, return true. There's a question, this only works because there are no duplicates. Yes, we don't allow duplicates for now. It's a simplified implementation. If you allow duplicates, then obviously all of this may get more complex. But so far, we don't allow this. We will later come back to this implementation and make a couple of changes to it. But first of all, we will be looking, we'll be looking at our slides, and this is just, there's one slide of code that I have skipped so far, but because we will later discuss this, but you see the code for find value and insert. Now, when you have a tree, you will come across something that is called traversing. And traversing, it actually means something like tree search or walking the tree. And tree traversal is just some form of graph traversal, because a tree is a specific graph with some constraints. And when we traverse a tree, we want to have some process of visiting each node in a tree data structure, but each exactly just once. We want to be visiting all elements, but each element exactly once. And if you look at, for example, trees, there are different traversal algorithms. There's a whole order or a whole set of so-called depth-first search or depth-first traversal algorithms. And there's another one called breadth-first or level order. These terms, depth-first and breadth-first, they are, if you look into a graph course or something, they can also be defined in terms of graphs, not just in terms of trees. Then they are more generic, but this doesn't matter for now because we're caring about trees in this chapter. And for these depth-first traversals, there are 3 concrete ones, which are in order, pre-order, and post-order. And the other approach is breadth-first or level order. And we will now visualize them and discuss step by step what these different traversal algorithms mean. And then we will see how to implement them, because there are different ways how you can traverse the tree based on which part of the data of the tree you want to get first. Depends also on your algorithm or maybe your use case, what you want to do with this data. And for this, I will switch to the iPad, which just takes a few seconds to share. And then I will show you a sample tree. And we are looking at a sample binary tree. So tree traversal. We find exactly the same tree in the slides. So we have a root with value f. We have 2 children, and the children are B and G. B has 2 children, which are A and D. And D, again, has 2 children, which are C and E. And our G only has 1 right child. So the right child is I, and I has a left child, which is H. And we can see this is a binary tree because we have an F, and everything to the left of F is smaller than F. So if you assume that A is less than B, B is less than C, and so forth, and everything to the right, like G, H, I, are greater than F. And the same holds true for this B. A is less than B, D is greater than B, and within D, the C is less than D, and for the E is greater than D. And we have our F, which has the right child G. I is greater than G, and H is less than I. So, sorry, H is less than I. So we see this is a binary tree. The sorting actually holds true. And I will now discuss these 4 traversal ways with you. We are starting with, say, level order. For level order, we are starting with the root element, which is F. Then we are going to the next level, and we're taking in the next level, first the left one and then the right one. So F, so root one, and then we take B and then G until that level is finished, because you can imagine that we can separate the levels, something like this. So first F, then B, and then G. And then in the next level, again, totally from left to right. So we take the A, the D, and the I. And now it's your task, without looking at the slides, to tell me the remaining nodes if we in the chat, or the remaining values if I continue the level order traversal in this tree for the last level. So maybe just tell me the 3 elements I have left and in which order they would be appearing if I traverse in a level order way. We got the right answer. It's a C, an E, and an H. So C, E, and H. So this was level order. We will now do, let me think about which one I want to do with you. Say we'll take pre-order, because from this depth first search, we have 3 of them: in order, pre-order, and post-order. But I guess we're starting with post-order, which is maybe the easier one to understand. Sorry, pre-order is the easier one to understand. And pre-order means I'm starting with the root, or with that node value, F. Then I'm looking at the left element, which is B. So far it looks the same like level order, but the difference will come very soon. And then if my left element is it, and there is no children of the left element, I would then go to the right child of the root, which would be G, but B actually has children. And then I'm applying the same again. So my recursive approach is take my node value, then go to the left, and take that value. Once the left is totally done, go to the right one, and so forth. And we'll try this out now. In a few moments, we will see how to implement this. But B is not done yet, so I cannot go to G yet. So B has a left child, which is A. So I'm taking this one, but A has no children. Then I go to the right child of B, which is D. And for D, I'm again checking, does it have a left child? Yes, it does. So I'm going to C, but C has no more children. And then I'm going to the right child of E. So far, we have processed now the left subtree, because we have the F, then the B, A, D, C, E. And now we're applying the same approach to the right subtree. We have G, so we take our G. G has no left children, so we continue with the right. Then we go to I, we grab that value. And then we look at the left, which is H, and we're done, because then there's no right child of I, and then we recursively, or we terminate the recursion step by step, and we're done. So this is something that we call pre-order. We will implement this later, and we'll see it's fairly easy to implement this. Then we have in order, and after this post order, and they work almost the same, but just with a slightly different order of when we do which operation. So with in order, I'm actually first looking at the left, then at my current value, and then at the right. So remember, with pre-order, I first looked at my current value in the node, then the left, then the right, and with in order, I'm first looking at the left. Once I'm done there, at my value, and then to the right. So for F, I'm looking to the left, which is B, but here again, I need to think recursively, and I cannot take value B yet because B has children. So I'm going to the left, and the left has no more children. And then I'm done with the children of A because they don't, or the left child of A because A has no children to the left or no child to the left. Then I take A, and then I would take the right child of A, but there is no right child, so I'm done with this subtree around A. So A was the left child of B, and then I take value B, and then I'm looking at the right of B. And then I'm looking at D, but D still has a left child, which is C, and C has no more children, so I'm taking C, then D, and then the right, which is E, because E is a leaf, so no left or right child, and I'm done with this. I hope you got the pattern, and now, again, without looking at the slides, tell me which, I have 4 nodes left that and I need to take their values, and just write me the order in which you think this works now, because we've seen it on the left subtree and it's a recursive algorithm. So it should be fairly easy for you to apply this to the rest of the tree. If you have a guess in which order this would go, got a first guess? Maybe you want to take a little bit more time to think about this, without looking at the slides, obviously, please. So we've done this for the left of the root. Then actually we take the root value F, and then we apply all of this to the right subtree of the root. So we look at G. There's nothing to the left of G, so there's nothing I can do. Then I take the value in G, and then I go to the right. I go to I, but I still has a left child, which is H, and H has no left child, so I can take value H. There's nothing to the right of, or no right child of H, so I can finish here, go back to I, and for I, there's no right child to further evaluate, and then I'm done. So this is in order, and for this tree, so I'm actually getting them just in a sorted order. So A, B, C, D, E, F, G, H, I. And as there is a pre-order, the last one is actually called post-order. And for post-order, I'm first looking at the left, then the right, and then my value. Remember, for pre-order, it was first my value, then the left, then the right. For in order, first the left, then my value, then the right. And for post-order, first the left, then the right, and then my value. So for post-order, we can, again, start with our tree. F has a left child, B has a left child, A has no children, so A is actually for post-order the first one. Then I cannot take B yet because I need to look at the right side of, or the right child of B. There is D, and D has children. Then I go to C, and C has no children, so I'm done with the C. Then I take E, which is the right child of D. And then I have traversed or explored the left child and the right child of D, so I can eventually take D. For B, I have now looked at the left and the right subtree, so I can take B. And if you have a guess how to continue this for the remainder of the tree, send it to the chat because there are 4 left, 4 values, and just help me to bring them in the right order. And we will then compare your solution. One student already sent this here to the chat. I'll give you a few seconds to think about how to apply this recursive algorithm. But we got one answer, and we'll compare this now. So we've done this for the whole left subtree of f, and we need to do this with the right subtree of f. That means at the very end, once we're done with all of this, f will come, because we're doing the left of f, then the right of f, and then the actual f. And f is then the last value for post-order traversal. Then we're looking now at the right subtree of f, which is g. G has nothing to the left. Then let's continue with the right child of g, which is an I. And I has a left child. So we do the left child. The left child has no more children. So h we can take. Then we want to go to the right child of I, which doesn't exist. So I'm done. Then I can take I. And for g, I have now looked into the left of g, which doesn't exist, and everything to the right of g. That is done. Now I can take value g. And then when I looked at the root, I have finished the left and the right of the root. Now I can take the actual root value, f. So it's A, C, E, D, B, H, I, G, F. So we've now seen 4 ways to traverse the tree, and you're wondering which one should you pick when? Well, this totally depends on your use case. It's just 4 ways how you can traverse a tree. There's a little bit of more coming now, and then it will be maybe more clear to you which ones you would pick when. But it totally depends on your use case, which data you have structured, and in which order you want to go through it. And for example, before, when we looked at how we, when we had this mathematical expression, obviously we first need to evaluate the whole left, the whole right, and then apply the operation. So now you can maybe have a guess which one we would take for evaluating this mathematical expression before. But depending on the data on your use case, there's also good reasons to do level order or in order or pre-order. It purely depends on your use case and what you want to do. We will now continue with the coding, and we will try to implement these traversals. We'll start now with in order. Actually, we're not implementing in this course level order. We're implementing those 3 depth first ones, so in order, pre-order, and post-order. And I'll show you now how we can implement this. We're just going back to the code from here. And we will now implement a new method that we just call print. So print is just an in-order print. Later, we will implement this in a better way, but we're just starting with the most simple one possible. So we say, if there is something in the left, well, then print or recursively print what's in the left. And once this is done and I have finished the left, then I'm actually printing my data value. And if there is something in the right, I'm printing what's in the right. So this is just my in-order implementation, because we first look at the whole left, then at my value, and then at the right. And obviously, recursively, as we just saw. Are you surprised that the in order can be implemented that easily using recursion? If you feel this is surprising, maybe thumbs up or thumbs down. if this is not surprising to you. I just want to see if anyone is not surprised or if someone else is surprised. And there's nothing wrong with being surprised or not being surprised, because before on this example, it all looked quite complex. But we see, in fact, once we understand it, we can describe it extremely easily using recursion. And now I want to build the tree from before, the one I had visualized on the iPad, where I said my node is an F, and I want to build exactly the same tree as before. And I'm just typing this from my slides. We need to insert them in exactly this order that it works, because we said we have a left child B, and then we need the A that is less than B, and our D is greater than B, and then D has subchildren C and E, and for the right, it's GIH. If you change the order of these characters in the string and you're inserting them in a different order, so because what I'm doing here is I say I have a string, and a string is a sequence in Python. So I go through the string. That means in the first iteration, I have the B, then the A, then the D, then the C, E, G, I, H. And then each time I'm inserting this character. If I insert them in a different order, my tree will look differently. And this may be a problem for sorted trees, or for search trees, but this is something we'll be discussing later today as a downside. But if I go through the characters exactly in this order, I'm creating exactly the tree from before. Feel free to try this out on a piece of paper on your own. And if you change the order of these characters, you will get something, you will get a different tree. But now comes the interesting part, because we can now try to print this, and it's in order, and we see it's A, B, C, D, E, F, G, H, I. And this is exactly the in-order traversal result we also got before when we tried this manually on the iPad, because I started it and you helped me to complete the in-order, which was your task. And there we also saw it was just sorted, that it was A, B, C, D, E, F, G, H, I. So we have actually implemented the in-order here. Anyone has an idea of how I could implement a pre-order? So I have done this here to implement in order, and in order was first the left, then my value, then the right. Anyone has a suggestion of how I can implement a pre-order? If you have, maybe raise your hands or turn on your microphone or something, or send this in the chat of how I can implement a pre-order, for example. Or maybe just green sticker if you have a clue or not. We got a proposal now in the chat. It's actually fairly easy. If you want a pre-order, just move this print of my self data to the beginning of the method, then do the left part, then the right part. If you want a post order, do the left part, then the right part, and then move this print to the end of the method. So these three traversals that are depth first, they're fairly easy because I just need to move this one print around. It isn't really that complex. But this is also something in the coursework I'll be mentioning later. So I will go to the slides now, and there's a little bit of more theory, and then we try coding something new. So this is just a tree I had on the iPad. You have it here again. And we created our sample tree and we implemented the in-order traversal. Now, this one here is a very simple way how to implement the in-order. It's really not a smart way of doing this. And there are lots of reasons for this, because imagine if our tree is huge, then maybe printing this tree could take very long, or going through the whole tree. But maybe I just want each at a time, one more element, and I want to do this in a smarter way. And for this, I will need the concept of iterators and generators. When this course started and I provided you with an intro to Python, there was also some further reading. And I asked you to read the further readings in the Goodrich book about Python, and there was something about iterators and generators. Who actually read this, or who still remembers what was in the book? If you do, maybe just send a thumbs up or something if this is something you remember, or a thumbs down if you don't remember. I'm just curious to see if anyone remembers these concepts of iterators and generators or not. So one does, one doesn't. That's totally fine. So we'll be now looking at this terminology of iterators and generators. So an iterator is an object that helps us to iterate through a series of values. And for example, if we call this iterator I, and we want to iterate over a data structure, it would initially refer to the beginning of that data structure. And then if I have an iterator in Python, I can call the next method or next function. It's a native function, and it would then return the current element that I'm pointing at, which would be the first element. If I call next again, I will get the next value. So each time I call next on that iterator, it gives me the next value. And once I have reached the end and I'm calling next again, I will get a stop iteration exception, which would then be the end. And I'll show you this soon in Python. It's very important. Iterators and generators, something we'll see soon, exist in many other languages as well. This is just how it's concretely implemented in Python. But you will also see iterators in Java or C++, whatever, because iterators highly generically are just something that go through a data structure for you, and each time you're calling the iterator, it will return you the next element, and it will return it and not just print it, because before we have printed it on the command line, maybe not too great if we actually want to process these values. So we rather want to return them, and then we can print them or use them for some other calculation. And to create an iterator on an object, I say iter of object. And actually, we can create multiple iterators for the same object. And I'll show you this now in Python. So for example, I have my data, which are values 4, 3, 2, 10, 50, and 9. And if you go through all these values, or step by step, you have written always something like for value in data, and you printed the value. So, and internally, in fact, this so-called for each loop uses iterators to do exactly this for you. You can try to emulate this now just in a very simple way. We can say iterator 1. It's an iterator on the data. And then I want to get the next element in I1, which is the 4, then the 3, then the 2, then the 10, then the 50, then the 9. And if I call it again, I get my stop iteration and I'm done. And this is actually implemented natively in Python in these for each loops. So you don't need to handle creating an iterator, calling next, and handling the stop iteration. Rather, this is done high level for you. And the good thing is you can even create multiple iterators on the same data structure. So for example, I have now 2 iterators, and I can say, well, I want to have next in I1, which is again the 4, 3, and 2, the first 3 elements. But that doesn't change my iterator 2, because iterator 2 still points to the beginning. It hasn't been used yet. And iterator 2 now returns 4 and 3. And my iterator 1 would now return the next element, because I've looked at 4, 3, and 2. So iterator 1 would return the 10. So I can have multiple iterators to the same iteratable object, with each iterator maintaining its own state of progress. These iterators are a preliminary for what we actually need now in order to do our in-order, pre-order, and post-order, because concretely, what we need is now a so-called generator. And generators are a very convenient technique for creating or feeding iterators in Python. And the generator is implemented in Python actually natively in syntax by using the yield statement, which is a keyword in Python. Has any of you ever seen the yield statement in Python? If you have, maybe thumbs up. If you have never seen this, maybe thumbs down. So some have seen it, so I guess you have come across iterators. And those who have not seen it, generators, those of you who have not seen it, it's perfectly fine. We'll be discussing it now. And the generator actually generates always the next value from a sequence. And it would actually be feeding an iterator. And what are these generators useful for? I think I'll just show you this. It's a coding example, and then will become more obvious. Imagine I, for example, have my range. We said before, it's like I in range, and range could be 10, but range could also be a huge value like 1 billion. And if I want to go with an index I from 0 to 1 billion, for example, and my range is something I would first need to build, meaning the range would be something like 0, 1, 2, 3, and so forth. It could maybe take a long time to actually build this range first. It would lead to a huge memory consumption before I can actually start looking at the first element, because I need to build the whole list first. And actually, in Python 3, this is a generator. And the generator here means it first generates a 0. This is the first element. And I have an iterator pointing to this generator. When I say next on the iterator, the generator will generate the next element and then the next one. So step by step. So I don't need to build all these elements up front. Rather, I build one element at a time when I need it. So I don't need a lot of time in advance to compute all of this, and I don't need to waste my memory. Did any of you work with Python 2 ever? So we're using now Python 3 dot something. Has any of you worked with the old Python 2 environment? If you have, maybe thumbs up or thumbs down. So far, no one. If you look into Python 2, this actually generated like a list or a tuple or something up front in Python 2. And if this was a huge value, this would just take forever, or not, maybe not forever, take long and pollute your memory. And then when there was this transition from Python 2 to 3, at some point, they introduced an xrange function, which did exactly what range is now doing in Python 3. In fact, that it just gives me the next element that I need at that time. And I'll show you now how we can build our own range, at least a very simple one. We can say, we call it first n, and I want the first n values starting from 0 up to n minus 1. And the way I can build this in Python is I say, well, while num is less than n, so num is my number, it starts with 0, and I don't just want to go through a loop and build everything from 0 up to n minus 1. Rather, I want a generator. So, and for this, I use the yield statement. And then the yield statement means it gives me the value num at that moment when you call with an iterator next, it will give you the current value of num, and then it stops there. And when you call next on the iterator pointing to this generator again, it will keep running until the next yield statement. So the yield statement is simply something that stops execution at that point and returns that value, but later you can resume when you call next again. And what I'm doing here is simply I'm increasing num, and I'm saying +1, and then the next iteration of the loop runs, and in the beginning of this, it will stop at the yield statement. So I have just built my own range, and I'll show you now how this works. I can say for I in first n, like 10. I want to print this. And what it does internally is, we can explore this now. I can say I for iter. We create an iterator on first n. And I say next I, it's a 0, then a 1, then a 2, then a 3. We can also look at what I is. We see I actually refers, so the iterator refers to a generator object. If you ever have an iterator to some generator and you need all the values up front, you can do something like, we can say L, you can say list of I. This would actually build you a list with all the values from the generator. So here, what list would actually do if you pass an iterator in Python, it would go through all the elements until the generator is done, and then the iterator stops. But remember, if this points to some very, very large n here, or if this is unbounded, then this will not come to an end. So this is something you should rarely be doing in Python. Take all the values that the iterator can give you. Sometimes you may need to do it, but do this with care, because there's a reason why we have the concept of iterators and generators. Now you're wondering, what is all of this useful for? And there is a reason. I'm going with you back to just what we did here, because the way we implemented the in order was just some printing. And this was really not good, because it will go through the whole tree and then print everything. And maybe the tree is extremely big, or just keeps growing to the left, maybe infinitely long, then it's never coming to an end. This is not great. So we will now be implementing this as a generator. So self in order is now a generator. And I'm saying if there is something in the left, I'm doing something. If there is something in the right, I'm doing something. And in between, what we are doing, we'll see soon. And in between, I'm yielding the value from my node, because this is the value before I print it. Now I say yield, so means at the next time, next is called on the iterator, it will give me that. Now, what do I do on the left? Actually, I can say I go through all values in self.left.inOrder. And what this will do is it will yield, and then I will yield here. This looks extremely ugly, and we will improve this in a second. because what I'm writing here for all the values in self.left.in order, and when I get a value, I yield. I can write it like this if I wish, also for the right. So I say self.right.in order, and I yield the value. This works perfectly fine. It's just extremely ugly syntax. And you can actually use a concept in Python that is called generator delegation. And you would say yield from, and I'm just updating this, it's not done yet. You would here say yield from self.left.in order. And this is something we call generator delegation. I'll show you a slide in a moment with some theory about generator delegation. And I think like this, the syntax certainly looks nicer than before, because I don't have another loop, and within the loop a yield, rather I say I yield from some other generator. And we can try this out now. We can just, I just need a second to build this, or well, it's a long time ago, so probably I will just retype what we did before. So, because I need to create my nodes, I'll just need a moment to find this in my slides again. So just bear with me for a second. And then we're just rebuilding what we did before. So we said root is a node F, and we said for the values in B, A, D, C, E, G, I, J, we insert V. And now we can have an iterator. So I is an iterator on root dot, just need to check how this goes. This should be this. And then next I, so it gives me an A, then a B, then a C, then a D, and so forth. Because I'm calling root.in order, and it is a generator. And then I go through this until I'm eventually done. And we see at the end, I get my stop iteration. So, and since I have done this, I can also say, for example, for v in root dot in order, print v. And then if I use the for each syntax or for each loop in Python, it will internally create an iterator on this generator, and it will handle the stop iteration. So now we have built our in-order traversal much smarter, not just by printing, but by actually building a generator that each time yields the next value. And I can either print it or I can use it for some other operations if I wish. And this concept of generators and iterators, it's something we can apply to all of our other data structures as well, if we wish. It's something we'll be seeing again when we look at hash tables in one of the next lectures, so in a couple of weeks. But feel free to apply this concept also to your lists and other data structures we had built so far. We didn't discuss it earlier because I wanted you to become comfortable with Python first before we look at iterators and generators. But it's something that is totally not constrained to just our trees or hash tables. So this was the ugly way or the old way of using or by yielding something that comes from another generator. And then Python 3.3, which was about, I don't know, 10 years or a bit more, introduced this yield from expression, which allows a generator to delegate parts of its operations to another generator. There is a simple example here how to do this with range, but I've directly shown you how to do this with our in order. And this certainly, this yield from another generator looks nicer than this one. And this is something you had to do up to Python 3.2, but nowadays you can just do it this way. So there's a little bit of more theory for the last few minutes. Imagine you have a problem like this. Your task is to invert a tree. And inverting means I have a root which is 4. It has children 2 and 7. Child 2 has children 1 and 3, and child 7 has children 6 and 9. And an inversion of a tree would look something like this. The root stays where it is, but I'm flipping the left and right children, and I'm also flipping the children of the children, and so forth, recursively. So 7 and 2 are flipped, and the 7 had children 6 and 9, so their children will be 9 and 6. And 2 had children 1 and 3, which would be then 3 and 1. This is what a tree inversion would look like. If you see this for the first time, if you think this should be very easy to implement, thumbs up. If you think this looks extremely complex, maybe thumbs down. And maybe, so there's a majority for thumbs down. And it is true that this looks confusing. There's a very famous software engineer, Max Howell. He's actually the one who created Homebrew. Homebrew is a package management system for Mac. Any one of you uses Homebrew on a Mac? Maybe thumbs up or thumbs down. Homebrew is a very helpful package manager, like you're used to from Linux with apt-get or others. And there was a lack of this in the early days for Mac, and Max Howell implemented Homebrew as a package manager. If you come from the Windows world, probably you have no clue what a proper package manager is. Something that comes originally or has been very popular in the Linux world, and on Mac, Max Howell introduced this. And that's why he's well known in the Mac community. And he actually wrote in 2015, he applied for a job at Google. And there, one of his interview questions was he should implement inverting a tree. And it's something he didn't manage, so he didn't get hired by Google. And he wrote a Twitter post and was very angry about this. He said 90% of the Google engineers probably use Homebrew, but he couldn't invert a tree, so he was not hired. In fact, it takes a few lines of code, maybe under less 10 lines of code, if you implement a tree inversion. And this is also some of your homework, or coursework. So there is the trees chapter in the coursework, our tree implementation we have done so far. For in order, we've done the printing, we've done the generator, and it's your task to also do this for pre-order and post-order. But we've talked about the printing already, so it's fairly easy to extend this to pre-order and post-order. And then there's another problem about inverting a tree. So you're passing the root, and it's your task to invert the tree. Inverting the tree means you flip the left and right child. You need to check if there is a left or right child. And if there is, you also need to look into the left and right and then flip them and do this recursively. You just need to pay attention that you're not trying to invert something that doesn't exist, like you have no left child. So that left child, you would flip with the right child, but the child that has no children is something you wouldn't further be inverting. Try it out. It sometimes appears in past exams. How to invert a tree is one of the tasks. Here you can get some practice, and if you apply for a job at Google and they ask you this stuff, then it's something you can certainly manage. There's a lot of criticism about getting hired at Google because some people claim they only ask you or largely ask you questions in interviews about the foundations of algorithms and data structures and not very advanced questions, or not many of them, like about machine learning. But hiring at Google, they believe that if you understand the foundations of computer science and algorithms and data structures very well, then you can adapt to lots of other things. There's a lot of criticism to that approach. There are probably some good reasons to do it that way. I don't know. I have some friends who work at Google who passed this. From what they told me, my understanding is probably it's easier to get a job at Google after your first or second year at university, because you still remember all of these foundations. And once you actually apply for after your master's, you have learned a lot of advanced stuff, but you're maybe not that fluent on the foundations anymore, then it may be more difficult to get a job at Google. And you need to spend more time on practicing for this. So this is what I've been told by multiple people. Google applies a lot of science to their hiring process. So they claim it works this way, and this is how they could find the best people. I don't know, not my invention. But doing the inversion here is probably something that will take you a little bit of time, but once you have implemented it in less than 10 lines of code, you will see it's extremely easy. That's why it's a coursework problem. There is another tree problem that I represent a tree here as a list, actually. So these are more complex trees. I have a left child and a right child, maybe more children, so child 1, 2, 3, and so forth. And each child is represented as a sublist in my list. And I have sublists and sublists and sublists, and your task is to flatten the tree. That means to turn this tree actually into a proper list. Will take you maybe a little bit of time to understand it, or you can try to visualize this tree. It's a slightly different tree format, and your task is to flatten the tree. And this, again, looks very complex, but if you use generators, especially a yield and a yield from expression, this will be, again, less than 10 lines of code to actually flatten a tree. If you work with trees in the real world, you will probably not be implementing trees from scratch. Rather, you would use professional tree libraries that offer you lots of features for far more complex trees than the ones we have seen today. In Python, one of many of such packages could be any tree. You can pass certain information to the nodes, you can connect them, you can print them. There are maybe more algorithms to work with these trees, and so forth. I was asked today by a few students about the exam. And as you have noticed, we are progressing with the course. We have finished about 2/3 of the lectures or something like this. We have quite a few more lectures. Nonetheless, we are progressing, as you can see. And that's why I want to say a few information about the exam. You find all the past exams in my Nextcloud directory. And there's every summer term, there is an exam. And for those who don't take the exam or fail, there is a reset exam in the winter term. And in the reset exam, I always assume just the summer course that we had taught before. So if you don't take the exam in the summer or fail, you can take the reset in the winter. The exam this year will be in July. There's already a date announced. You've seen it. The exact date is, I'm just checking which day it is in July. The exam is the 12th of July. And my exams always have the same structure. There are 3 problems, and you're supposed to work on 2 of these problems. Each problem carries 25 points, so you can score up to 50 points. And now you're wondering, how do I convert points into a mark? There's also a sheet for this in my Nextcloud, but I'll quickly show you this. So my exams always look like you have 3 problems, you pick 2, so you can score up to 50 points. If you work on all 3 problems, the best 2 problems will count. But I really urge you, focus on 2 problems in the exam so you have a choice. And if you have finished 2 problems in those 90 minutes and you still have time left, then work on a 3rd problem, but don't scatter your efforts early on throughout the 3 problems, because only the best 2 problems count. So for this student here, the student scored 20, tried all 3 problems, scored 24, 5, and 20 points. So the best 2 are 24 and 20, which is 44. And I convert your points into a mark. You have seen in the coursework, there's also an exam bonus problem. And if you finish the exam bonus problem as one of the lab problems, concretely, that's the exam bonus problem here, 12.6. It's about decision tree learning, something we'll do in the next lecture. If you do that correctly and in time, you will get 5 points on top. So if this student got a bonus, you would then have 49 points plus 5 points. And I convert the mark by using this equation, where I convert the points into a mark. I say 60 minus your points divided by 10. So you can score up to 50 points. 60 minus 50 is 10, and 10 divided by 10 is a 1.0. So the best mark possible in the German grading system. A 1.0 is like a A+ or something, and a 4.0 is just a pass. And if you score 49 points, you have a 1.1, but 1.1 is not a valid mark, so it's a 1.0. I convert this to your advantage. A 1.2 is also not a valid mark, because valid marks are only 1.0, 1.3, 1.7, and then 2.0, 2.3, 2.7, and so forth, up to 4.0. And you need 20 out of these 50 points in order to pass. So you need 40% for a pass. If you have less than 20 points, you will fail. And the exam bonus only counts if you have passed already. So you need to score at least 20 points, and then you can get the bonus on top. But the bonus will not save you from failing. And there's a question here as well about, so the exam bonus problem is totally up to you if you do it. It's a good practice and it will improve your mark if you pass. The mandatory problem is absolutely mandatory. And when you registered for the exam, you had 2 things you could register for, not just the exam, but the other one is called Leistungsnachweis or Übungsleistung. This is the mandatory problem. You also had to register for this, or you got pre-registered for this. If you forgot to register for the mandatory problem in Primus, still try to register or write a center of studies. Depending on your degree program, this is either called Leistungsnachweis or LN, or ÜBL or Übungsleistung. And this one you need to pass, otherwise you cannot sit the mandatory, or otherwise you cannot sit the exam. So this is mandatory, and the problem P minus 13.50 is a problem not from this coursework sheet, but from the Goodrich book, because this is practice 13.50 and it's in the Goodrich book. It's about pattern matching algorithms. This is something in general about the exam. And in the exam, there are 3 problems. You see all the past exams in my Nextcloud. Last year, there were some students from the German language program. They claim they struggle with questions in English. And that's why starting last year, starting the recit problem from last year, I have directly put in translation of these questions. So for example, problem 1, it's binary search and bisection, or the German translation. And I always post a question in English and then the question in German. Until the exam before, there was usually an extra document where I had put in the translations, but starting the last reset exam, I always put in the question in English and then in German. And it will look the same this year in the exam, that there is an English question and the same question translated. Ideally, everyone answer the questions in English because the course is in English, so you know the terminology. However, if English is a major problem, look at the German question and write the answer in German, or write the answer in English. And if you lack some words in English, then use the German words, but stick as much as possible with English because we've done all the terminology here in English. And then you see there are 3 problems, and each problem carries 25 points. And a problem has subproblems like A, B, C, whatever, and you're supposed to write in this box here. And in terms of helper tools, you have to bring a calculator, a simple calculator that can do fractions and logarithms, but not a computer algebra system. So not a super fancy calculator. That's not allowed, and you're obviously not allowed to use your phone as a calculator. And you can also bring a one-sided handwritten A4 note sheet. So if you have any notes that you need for the exam, that's why you can bring a A4 note sheet, and you can have handwritten notes on one side where you may want to put some definitions or something that you just cannot remember, maybe the definition of the master theorem or some equations. But it needs to be handwritten, not like typed on a computer and printed. Because if you handwrite this and collect all the notes, it will certainly make your studies easier, or your preparation easier for the exam. And you find all the past exams in my Nextcloud directory. And the reset exam last year, one problem covered binary search and something called bisection. Bisection is a new algorithm, but it's explained here. And with all your knowledge about the binary search, it's fairly easy to implement this. Then the second problem covered quantum computing, recurrence relations, and decision trees. Quantum computing and decision trees are still to be discussed in this course. And then graphs and lists was problem number 3. And graphs and lists is something we have already finished a couple of weeks ago. In the next lecture, we'll be looking at more advanced search trees, not just binary trees, because these binary trees, they may run into some problems when you store your data in, and we'll see this in the next lecture. And we will also then look at decision tree learning as an application of machine learning, and we will see what these trees can be concretely used for other than foundations of algorithms and data structures. I also pinged you in iLearn about the schedule of the next few weeks, because the Fridays in 1 week and in 3 weeks, they are officially lecture-free days because of the holidays around them. But the Fridays in 1 and 3 weeks, we do the lecture at 8 o'clock in the morning and via Zoom, and it will be recorded as usual. I've sent you this in iLearn. Have you seen the message? Maybe thumbs up, thumbs down if you're familiar with the schedule. So we do a 90-minute lecture in 1 and in 3 weeks, plus a Zoom or an online lab session, even though they are lecture-free days. Or you're wondering, why do we do this on the days that are officially lecture-free? Because the Friday in 2 weeks, I'm at a conference, and I don't want us to miss a class 3 weeks in a row if there are 2 lecture-free days because of holidays around them, plus 1 Friday I'm at a conference. So that's where we're taking these 2 lecture-free Fridays, and we're doing the lecture from 8 to 9:30 approximately. And after that, I'm still in Zoom if you have any questions on the lab. And I think like this, we can progress very well in May, despite all these holidays and my 1 day where I'm at a conference. There's a question here about the exam. If if you can print the notes, if you write them with a pencil on the iPad, that would be okay. But if you handwrite on the iPad and print, that's okay. But don't type on the iPad or a computer and print, because that's forbidden. So, are you okay now with the further setting of the coursework and the exam and the marking? Maybe thumbs up, thumbs down. I know we needed a little bit longer today, but I wanted to discuss this and make sure you're registered not just for the written exam, but also for, depending on your program, if it's called Leistungsnachweis or Übungsleistung. If the registration has passed or you're unable to find this, please don't write me about all these registrations for exams. Always write the Center of Studies, because they are there to help. I don't have access to Primus. So even if you write me that there are registration issues, I'm unable to help because I don't see this in Primus. I only have access to Primus to add the marks after the exam. So make sure you sign up for this. Or write a Center of Studies in case of any problems, and work on the mandatory problem. The mandatory problem is independent from all the algorithms we're discussing. By now, you have enough background in algorithms to read this in the book, these pattern matching algorithms, and to work on this in, you can either do this alone or in a group of up to 4 students. And if you work in a group, make 1 submission per group where you put all the student IDs and names in that submission, that I know who the group members are. You can do this alone or as a group for the mandatory, as well as exam bonus problems. So you can do different groups for the problems. That's totally up to you. And what exactly I'm expecting is written here in the coursework sheet. So next week then, on the, which is again officially lecture free, but because there is a public holiday on the following Monday, we're meeting here online at 8:30, at 8 to 9:30 for the lecture. And then we'll be doing an online lab session after this. So enjoy your weekend and see you next week. Take care. Bye-bye.